Okay. Good afternoon, everyone. I'm Arnab, and I'll present our work TWO-IN-one-SSE, first scalable, storage-efficient, searchable symmetric encryption for conjunctive and disjunctive Boolean queries. So that is a really long name, so we simply call it TWO-IN-SSE. And this is a joint work with Devadrita, Ayushi, Shikhar, and Devdip. So as we know, SSE has emerged to be a really attractive research area in applied cryptography. But the initial works of SSE are focused on single keyword schemes, and later, as the development grew, we saw that it is highly restrictive to really to be accepted as a potential solution for practical encrypted search. So for the encryption for the further scripts that has been proposed is mostly focused on multi-keyword queries and mostly Boolean queries, which are needed for processing more complex querying that we encounter in practice. And for that, we need at least the basic queries, basic conjunctive queries, and basic disjunctive queries. So currently, the SSE research has mostly focused on conjunctive queries. There are state-of-the-art algorithms which attain optimal sublinear search over it and linear storage over it. But as we see, disjunctive queries are not that well explored. So the current constructions that are they're mostly dedicated to the there are very few constructions which are dedicated to the disjunctive queries. The well-known OXT construction, which is a similar construction for conjunctive queries, can also process disjunctive queries, but in a very inefficient manner. And the only known popular disjunctive construction, IX, that has sublinear search over it for it, but it has very high storage over it. It is quadratic in terms of the plain database. And as a derivative of this construction, CNF filter also incurs very high storage over it. So naively, we can see that if we want to process disjunctive queries naively with SSE, either we can compute the trivial union of the keywords in the query, but that is very inefficient and prone to leakage. And otherwise, we can transform the disjunctive query into a equivalent one using De Morgan's law, but that is very inefficient, and there are a few things like the negation of keywords are not well understood, and the distribution of the keywords also changes in the database, which is really problematic in query processing. So IEX circumvents these things by adopting an inclusion-exclusion based approach, but in this process, it attains sublinear search overhead, but at the same time, it incurs quadratic storage overhead and also very high search overhead for conjunctive queries. So in that sense, the area of SSE research where there is a single platform which can efficiently process both conjunctive and disjunctive queries with optimal storage overhead is still unexplored. So in this work, we proposed TWO-IN-SSE, which is a dedicated construction for disjunctive queries, which can also process conjunctive queries very efficiently, and it incurs linear search overhead for the encrypted database. And at the same time, it has sublinear search overhead for disjunctive queries. And we introduce a novel concept called meta keywords. That this is a transformation-based approach which basically transforms a disjunctive query into an equivalent expression of conjunctive keywords, some new keywords which we call meta keywords that we'll subsequently see. This is different from the De Morgan's law. We'll see how this is done. So the core idea is like this. So we have a disjunctive query Q equal to W1 or up to Wn. We want to transform it into an equivalent query of Q equal to W1 dash and up to Wn dash. So this W1 dash and up to Wn dash, that we want to transform the query into in this way such that we can express such that if you query this new expression using a conjunctive searchable symmetric encryption scheme, we'll get almost the same result as of querying the disjunctive query that we had in the first place, W1 or up to Wn. So how do we do this transformation, or how do we construct these meta keywords? So to understand that process, we start from the query processing first, so that will give you a better idea how this is done. So think of a database consisting of 12 keywords, W1 to W12, and we have a sample query of W1 or W3 or W6 or W10 or W12. So visually, you can see that if we order all keywords in a row and we represent the keywords that are present in the query as dark boxes, so you can see if we construct the new rows of keywords as below, where we keep only in all those rows we keep only those keywords that are present in the query, and each of these rows subsequently, in one at a time, we keep a stretch of absent keywords. So when we AND this all together, it will give you those absent space of keywords. So you will get back your own query. So this is a visual representation of the process that we are employing here. So in practice, this is basically done by computing a union of all those keywords as and all those keywords which are present in a particular row, and where a particular stretch of keywords is absent. So we call this new representation as the meta keywords. So when we will, so if we AND these, we'll get the query back, and if we query these meta keywords as a conjunctive expression using a conjunctive searchable symmetric conjunctive SSE algorithm, we'll get almost the same result as of querying the actual disjunctive query. So actually, this process returns a superset of the actual result. So this is not an exact solution. There are some spurious IDs present in the result, but we did experimentally show that this percentage is very less, and you have the actual result IDs, all actual result IDs present within the solution, so you can locally filter out all the other spurious IDs. But unfortunately, this plain solution, this plain transformation this also incurs quadratic overhead, and in worst case, it incurs linear search overhead. So to overcome that overhead, we further optimize this process. What we do that we partition all the keywords into specific fixed with bins, and we run the basic transformation process for each of the individual bins. So what it does, if your size of the bins is fixed with and relatively small, you will have quadratic overhead here, but that is constant. And at the same time, the number of bins will be constant. So if you run this entire process in this manner, this will lead to a linear overhead in practice. And at the same time, your search overhead still remains sublinear. So the final combined platform works like this. For the disjunctive queries, you transform the database according to the previous process I just talked about, and you generate the meta keyword encrypted database. And while querying, you first transform the query as I showed in the visual process, and you query those meta keywords over this meta keyword database, meta encrypted database, and you get back the exact same result, almost the exact same result. And if you combine this in a single platform, since you are querying the database using a conjunctive SSE scheme, you can run conjunctive queries using the same algorithm that is underlying the disjunctive process. So you can combine that in a single platform without incurring additional algorithm for conjunctive queries. So as an implementation result, this linear storage overhead is certainly much less than the previous state-of-the-art IEX. And depending on the bucket size, as we see, this storage overhead varies. So for our application, for our implementation, we chose n equal to 10, and for that we attain the previous overhead there. As a search overhead, this TWO-IN-SSE performs as good as OXT, which is less. In our experiments, it incurred less time than IEX. And for disjunctive queries, it performed almost as equal with IEX. With the difference is because IEX is purely symmetric key scheme, where we use OXT, which has costly ECC group operations in that. And as I said, there are some spurious IDs present in the return result, but that is bounded within the 85%, 15 to 10% of the entire result set. As in conclusion, so we provide an efficient low storage dedicated solution for disjunctive queries which can also process conjunctive queries efficiently. And if you expand your query processing method, you can also process CNF and DNF queries very efficiently. And our algorithm incurs linear storage overhead and sublinear search overhead. And the security of this scheme is strictly inherited from the underlying conjunctive SSE scheme. As future directions, we would like to extend this to a dynamic setting, but that is quite challenging at this moment. So we leave that as an interesting future work. And we would also like to look into reduce number of spurious IDs in the final result set, and also the communication overhead also a bit high in our case. We would also like to look into that matter. Thank you very much. If you have any questions, I'll be happy to answer.
Thanks, Arnab. Please do not forget to ask your questions on Zulip. And for Arnab, this was a great talk, and you're already moving the expressiveness of search forward. But do you have any plan to going further than this and supporting a more subset of search languages such as Lucene or more advanced searches?
Right. We were naturally the next step would be efficiently implementing CNF and DNF queries, because if you want to have more complex queries, these are the places that you have to do it very efficiently first. We were working on that, but since this can process these two, we are looking more into that part first. Then we'll explore what other complex queries that we can process with this.
Thanks.